In today's video, I am not going to be starting from the very beginning. I will assume that you know a lot of stuff. This is all of the binomial theorem stuff for AASL, and we are going to talk about the AAHL part of the binomial theorem today. So here is a summary of all of the things that I am assuming you know. This is the Pascal's triangle, which is a quick and convenient way for you to get the binomial coefficients that you need for expansions such as this one, x plus y to the power of 5. You're going to read this line of coefficients, 1, 5, 10, 10, and so on, from the line of the Pascal's triangle. In the meantime, the exponent of x is going down, the exponent of y is going up. And in case you want a bigger exponent, like 12 in this example, maybe you don't want to write down a big triangle. So there is another way to get to those coefficients. Of course, it's easy to guess that the line of the number 12 starts with 1, 12, and then there's a dot, dot, dot here. So pretend that the term that I actually want to look at is the term that has x to the power of 5 and y to the power of 7. Then the name of that number in the triangle is 12C5, but you don't need to build the whole triangle in order to get to the 12C5 because you have that formula over there. The formula is 12 factorial over 5 factorial times 7 factorial, because 7 is 12 minus 5. If you are okay with all of this, let's move on. So if you're not, I highly recommend that you go watch another video first. I'm going to link it in the description. But there is one more comment from that video that I do want to repeat here because this is going to be very important. It's the fact that whenever you use this formula for the binomial coefficients, there is a big part in the end that cancels out. So that's the r factorial part that remains there. The whole n minus r factorial gets canceled out with the end part of the n factorial from the top. And in fact, the only reason why we even put it in the formula, if it's going to cancel out every time anyway, it's so that we are able to call the numerator of the formula just n factorial, because it goes all the way down to the 1. Otherwise, it would be more strange to say that in the numerator we have to start at the 12 and then end at the 8. So it's just more convenient to call it a factorial. But it does always cancel out. And when it cancels out, the amount of numbers remaining is the same as in the numerator as well. So in this case, you have 1, 2, 3, 4, 5 numbers in the denominator, and also 1, 2, 3, 4, 5 numbers in the numerator. The denominator is a factorial. It's the r factorial, but the numerator is no longer a complete factorial. It starts at the 12, but then it stops somewhere in the middle. I made that comment in the other video because I was also using this fact. Over there, I used it in order to do some fancy limit tricks to get to the Poisson distribution. And today I'm going to use it for a completely different purpose, but it's the same comment. So that said, let's erase all of this and move on to what we want to do today, which is the high-level side of binomial theorem. So the thing is that up until now, we have been using this to expand binomials like x plus y to the power of something that made sense, right? A natural number, x plus y to the power of 5 is x plus y times x plus y, so 5 of those terms. If it was 12 of those terms, it would be more boring, but it would still make sense. Now, for the high-level side of this, we are going to start to do some crazy stuff. We are going to put exponents that don't quite make sense. So let's start slowly. By putting a negative number in the exponent, it doesn't really make sense because you can't have a negative 1 times that factor of x plus y, but it's going to get worse than that very soon. Negative 1 is not actually such a bad exponent. We do know what power of negative 1 does. It's just a fraction. So in order to use this as a first example, I don't actually want to treat it as x plus y, like the whole generality that it can be something plus something else. I'm going to work on a more special case. I'm going to look at 1 plus x. So here is 1 over 1 plus x. Of course, we know this identity is true, but that's not what we want to do. We are trying to expand that binomial to a power as a sequence of terms that are being added. We want to make it look like we were just doing in the binomial theorem. The same thing that was happening in cases like when the exponent was 5. We want to do something similar for -1, and that's not what that looks like. But this is an expression that should remind you of something else. You have seen this before. I want you to look at the 1 plus x as 1 minus x for a moment, because now this should remind you of something that you've seen before. This is the formula for the sum of an infinite geometric sequence. More specifically, an infinite geometric sequence with the first term equals to 1 and the common ratio equals to -x. So, okay, let's write down what that infinite sum looks like. It looks like that, which does look a lot like the x plus y to the power of 5. It's the sum of a bunch of terms. Of course, we started at 1 and we're multiplying by the common ratio -x each time. That's why these signs are alternating, and so it's like 1 minus x plus x squared, and so on. But the difference between this and the exponent 5 case is that this never ends. This is an infinite geometric sequence that we are adding to get to this formula. There is a restriction here, of course. Infinite geometric sequences can only be added when the common ratio has an absolute value which is less than 1. So what we are doing here also has that same restriction. And what I want to do now is to just compare what's going on here to what was going on in 1 plus x to the power of 5. First of all, they both start with 1. Then the second term here was 5x, and we know that's because 5 is the next number in Pascal's triangle when the exponent is 5. But this is also 5 times x. And here when we do -1 times x, we also kind of get -x. So that's kind of weird, but let's pretend that the second term is the exponent times the x. But let's see what would be happening in the next term, because we have a 10 here, and we know that 10 was 5c2. And 5c2, like we mentioned, only has 2 factors on top and 2 factors in the bottom. In the bottom, it has the 2 factorial, and on the top, it starts at 5 and has 2 factors. It's important to look at it this way instead of looking at it like factorial over factorial times factorial, because you really don't want to talk about -1 factorial. It just doesn't fit into the definition of factorial, where you start from your number and then you subtract 1, 1, 1 until you get to 1. If you start from -1 and you start subtracting 1, you're never going to get to 1 because you're going the wrong way. So that is not the appropriate way to look at it. But this works. There's a 2, so it's a 2 factorial in the denominator. In the numerator, we want to start from the -1, which was the exponent of the binomial. And then after that, we only want one more factor because we want to have 2 factors. And this next factor should be, well, -2, because we are starting at -1 and going 1 to the left each time. So there you go, minus with minus is plus, 2 cancels with 2. This is just 1, which is the coefficient that we are seeing here in the x squared. And this is super weird, but it does work. Let's do it with 3. So I have a 3 factorial here. Now I want 3 factors on the top. The first one needs to be -1 because of this, and then -2 and -3 in the sequence. So at least for this very special case of -1, we can already see the pattern of what is going on, because everything is always going to cancel out. The denominator is a factorial, like 3 to 1. And on the numerator, you're going to get the same factorial going backwards, because instead of starting at 3 and going until 1, you start at -1 and go to the left. And this is going to happen for any number that you put here. So they are all going to cancel out in all of the terms. And the factors in the numerator are all negative. So depending on whether it's an odd or even number, the total sign is going to be odd or even. So the alternating signs are appearing because of that reason. So what I think I've just done is to convince you that at least in this case, if you think of it in this weird way, we get the same result as something else that we already knew, which was the sum of an infinite geometric sequence, which does make sense. So I did not explain why this makes any sense, but I did show you that at least in this case, they get the same result. What I'm going to try to do next is the same thing, but in a different example. So now instead of -1, we have -2. So we're going to start with 1, and then the next term is going to be minus 2x. And for the next term, which is going to get an x squared, the coefficient is going to be, well, minus 2 times minus 3, and that's 2 terms. So in the bottom, we have a 2 factorial. This cancels out with this, and the answer should be plus 3. Again, at no point did I explain that this process makes any sense at all, but this is the process that we were playing around with for the exponent of -1 case. So I'm just doing the same thing, and we're going to see what happens. 2 terms here, 2 terms here, those are the terms, so plus 3x squared. Now for the term in x to the power of 3, I'm going to need 3 factors. They're going to be -2, -3, and -4. In the denominator, 3 to 1, which is 3 factorial. So let's see, this cancels with this cancels with this, and I am getting a -4. That's going to be the pattern, right? Because for the next one, I'm just going to get one more factor here and one more factor here. This one is going to cancel out with this one, so it's going to be 5, but the signs are alternating again. So I already understand the results that this process is giving me for this example. Okay, we have an answer. What can we do in order to check if this is the correct answer? I'm going to try a couple of different things. The first one is going to be to go back to the -1 exponent that we had before, because I have a lot more confidence in that result than this one right now, because again, that is just the sum of an infinite geometric sequence. And this thing here is looking a lot like derivatives, right? It's 3x squared, 4x cubed. And by a very happy coincidence, this is almost the derivative of that. So let's just take a derivative on both sides of that equation. It's not exactly the same thing, because when you take the derivative of that, you get a minus sign in the front, which this one doesn't have. But that's the only difference. So we're going to get the opposite signs. Let's see. Derivative of 1 is 0. Derivative of -x is -1. Derivative of this is 2x. Yeah, all of the same terms, but with reversed signs. That is exactly what I expected to get. If you didn't want to do derivatives, another thing that you could do to check this one from that one is just to multiply that one by itself, because that squared is supposed to be equal to this. You may think that there is a problem with multiplying two things, each of which is infinite, but that's why when we are working with this kind of infinite polynomials, so to speak, we don't start from the biggest degree of the terms. Actually, we do the opposite. We start from the 1, and then we go up in the exponents, which is why I'm working with 1 plus x instead of x plus 1 for the original binomial to be expanded with these exponents. So yeah, I am multiplying an infinite thing by another infinite thing. So how do you do this distributive? You're obviously not going to be able to do first the 1 with everybody, then the x with everybody, because every time I say everybody, it's an infinite number of things, right? So that's not how you're going to work with multiplication of infinite things. So when you have a product of two finite polynomials, usually what you do is all of the distributive first, and then you collect all of the like terms in the end. Here's the opposite. We're going to kind of start by collecting the terms and then distributing whatever terms we need in order to collect them. So for example, we want to get a constant term here. The only way we're going to get a constant term from this product is 1 times 1. But after that, we want to get a term in x, and that we can get in two ways. It's either this 1 times this negative x, or that negative x times this 1. Nothing else that you take 1 from there and 1 from here, multiply them together, is going to give you an x, because everything else has higher exponents. So that's it. 1 and 2 pairs that give you just x, and I'm collecting them. That's why there's a 2. Both of them are negative, so -2. And then you want to do the same for the next one, the exponent of x squared. How are you going to get that? Well, there is 1 times x squared, negative x times negative x, which is also positive x squared. And now there is a third one, which is that x squared with this one. So that's why there's 3 of them. Here's a 3, and hopefully you can already see the pattern. It's always going to increase by 1 because you get one more way to get the bigger exponent. Does this prove that the process works? Well, it is more evidence. It proves that it worked in this case. So now we have 2 cases that worked instead of just the one. And for now, I am going to leave it at that before we move on to even stranger exponents. The square root of 1 plus x is 1 plus x to the power of a half. And we are a lot more lost in the beginning of this example than we were in the previous one, because the exponent of -1, we kind of knew that it was a fraction and we know about the sums of sequences and all of that stuff. But a square root of 1 plus x, we don't have anything to compare it to. We're just going to go on blind faith here for a start, okay? Just 1 plus x over 2, that is the exponent times the x, like we were beginning before. And now for the coefficient of the term in x squared, we are going to start by taking 2 factors over 2 factors. The first of the factors is exactly like the exponent, and the second one is 1 less than that. So from half, we are going to go to -half. I'll simplify it in a minute. For now, let me just do the next one with 3 factors, which are half, -half, and -3 halves. I did x to the power of 4 as well, but this one is more difficult to find a pattern, isn't it? We do have the factorials in the denominator and the alternating signs, except for the first term, which should be negative but isn't. And there is a power of 2 appearing here as well that's going to be in a denominator, like 2 squared, 2 cubed, 2 to the power of 4. But there are stranger terms appearing. Up until here, you could say, oh, that 3 is going to cancel with that 3. But then over there, you get a 5 appearing in the numerator that doesn't have anybody to cancel with. So it starts looking like it's going to be one thing, and then suddenly it's a different thing, and the pattern is not obvious. I don't think that finding a pattern here is the most important thing that we should talk about right now. There is a way to write that with factorials, because the problem is that only the odd numbers are appearing in the numerator. So at some point, you're going to want notation for something like that, which is not quite 9 factorial, but it is all the odd numbers starting from 9. And the traditional way that people do that is by putting the even numbers in between as needed, and then you have to put them in the denominator as well. So now you have a 9 factorial on top, but on the bottom you don't quite have a factorial either, but you have all even numbers, so you can pull out a 2 from each one. So here you have a 5, 3, 2, 1 that you're going to treat as a 4 factorial. And here you have 2, 2, 2, 2, which is just 2 to the power of 4. Then you get that. Of course, I did it in an example. I didn't put a k or an n anywhere because, like I said, this is not the most important thing for us to do right now. If you want to have fun with it, go ahead. So what I want to do instead is 2 things. One, I want to suggest an application of this, like why would anybody ever want to do that? And second, I want to try to convince you that the crazy method that we're using is actually good. So the idea is that people can use this in order to calculate approximations for square roots, for example, of numbers that are not obvious. Like if I have the square root of 10, what is an approximation for the square root of 10? It's going to be 3 point something, right? Because 10 is slightly bigger than 9. So you call it the square root of 9 plus 1. Now, it may look like this one is going to be that one, but it's not. The 9 is going to be the one. Because here's the thing, the process is already complicated enough, and we are only working with 1 plus x. We are not working with x plus y. So we are always going to work with 1 plus x. If you have something else plus x, you just divide by that thing and factor it out of your binomial. So it looks like this. The 1 over 9 is the x. This is good because x is a small number, and we are dealing with an infinite sum of things, with increasing exponents of x, in order for this to mean anything, the x has to be small, because as you're putting it to bigger and bigger powers, it's getting smaller and smaller. So hopefully the final terms are going to matter less and less, and you can hopefully get a good approximation just by looking at a first couple of terms. So how good is this as an approximation? I'm just taking two terms. My calculator is telling me that this is 3.16666. The actual value of square root of 10 is that, so it's pretty close. We're getting an error in the third decimal place. If you add one more term, you get a little bit closer, and so on and so forth. You see what's going on. But of course, it would be an entirely fair question to ask, well, if you're going to use the calculator to do this, then why won't you just use the calculator to do that instead, just the square root of 10? Why do you need any of this to get an approximation when you can just get your machine to do it for you? But the thing is that somebody had to tell that machine how to do that. And this kind of thing, not exactly this process. I'm sure the calculator has been programmed with way fancier and faster stuff, but this kind of process on how to get approximations for complicated stuff is very important for making calculators. It's not for the user of the calculator, it's for the person who provides you with that tool. This is how that sort of thing can work. Okay, so that was kind of the application that I wanted to show you, and the next thing that I want to do is to convince you that this expansion is correct for 1 plus x to the power of half. And it's going to be a similar exercise to what we did in the other examples. 1 plus x to the power of half times itself, it's supposed to be equal to 1 plus x. So let's see if it is. The constant term is always going to come from 1 times 1. The term in x can come from 1 times x over 2 or 1 plus x over 2, so that's x. We're going well. And now the term in x squared can come from three things: 1 with x squared, x with x, or x squared with 1. Lucky for us, all of those things cancel each other out because we are not supposed to have any term in x squared. And I'm not going to do the rest of it. I leave it as an exercise for you to have fun. X to the power of 3 is also going to cancel out, and x to the power of 4. That also doesn't prove anything, but it's getting to the point where it would be a little bit annoying if the whole thing turned out to be false, because we already have a few examples that worked. So before we move on, I want to make a couple of comments about notation. First of all, at one point in the video, I know that I wrote negative 1c2 as if it was the same kind of thing as 5c2. And I would just like to ask you to please don't do that. This is not acceptable notation. The formula booklet does have NCR with the factorials, but it's just for n is a natural number. And then it uses that NCR notation for the formula for the binomial expansion in the standard level. But when it comes to the binomial expansion in the higher level, then he doesn't use that. What he does is a little different. So first of all, he doesn't write this explicitly, which is what we were talking about, factoring out the a so that it always begins with 1 plus x. So this isn't written in this exact way in the booklet, but you can see from the next formula that this is what he's doing, because this is the way that he writes it. You can see that the b over a became the x because there is a b over a here multiplied by the n, and then there's a b over a squared here, which is the x squared. But look at this. Not only did he not use the NCR notation for this, which he could have because this is just NC2 with the final factorials canceled out, but he didn't do that because in this formula he wants to allow for the n to not be a natural number, and he doesn't want to use NCR notation when n is not a natural number. So that's why I was saying that you also shouldn't do that. But the annoying thing here is that he didn't write anything else instead. He just gave us the first term and the second term and then ... and you have to guess how the pattern goes on. We already know how the pattern goes on, right? The next one would include an n minus 2 here and a 3 here, and then an n minus 3 and a 4, because it was all of those things that we were talking about. Now I realize that I still haven't proven anything, and maybe I will, maybe I won't, but don't worry because you don't have to prove it, okay? You just have to know that that's the way it works, and the exercise is going to ask you for a few terms, usually not many, and you just apply the process, you'll be fine. But what I want to point out right now is that there is another thing in the booklet which does not fit into this framework at all because it doesn't have any exponent, natural number, rational number, none of that, but it's still a 1 plus x. So it's an ln of 1 plus x. And what is in the booklet about that is the MacLaurin series for ln of 1 plus x. It looks suspiciously similar to the things that we were just doing. But the other MacLaurin series that are also in the booklet don't have a 1 plus x. As an example, here is the MacLaurin series for sine of x, which is in the formula booklet. Could he have done a MacLaurin series for sine of 1 plus x? Yes, but it would look horrible and be probably useless. So why is that happening? Why is ln different? I'm going to go through this a little bit fast because this video is not about MacLaurin series, okay? So it's a summary. Of course, if you already know about them, you will understand more, but I will try to be understandable. The MacLaurin series is a sequence of polynomial approximations to a function. They want to be better and better approximations. And the first one, if you just take the term x and forget about everything else, you're getting the approximation sine of x equals x, which might not sound like a very good approximation when you say it like that, but depending on the value of x, then it is going to be a good approximation if x is small, because y equals x is the tangent line to the sine function at x equals 0. Now, if you take the second approximation here, x minus x cubed over 3, you get a cubic polynomial here, which is a good approximation for sine of x in a slightly larger interval than the first approximation. And this keeps getting better and better as you get more and more terms. That is the idea behind MacLaurin series. This is what they are trying to do. Usually they will have all of the terms. The sine of x is skipping the even degree terms because sine is an odd function, but that's an accident. In general, you would have all of the exponents. And just like the linear approximation is a tangent line at x equals 0, if you get the next approximation, including up to the term of x squared, then you're going to be approximating your function by a parabola, which is supposed to be the best parabola to approximate that function at that point. In the same sense that the tangent line is the best line, because it has the same point and the same derivative at that point. So the best parabola would go through the same point, having the same derivative and the same concavity. Concavity is the second derivative. So when you get to the best cubic polynomial that approximates the function, what does it mean to be the best cubic polynomial? It means that it has the same value as the function, the same derivative as the function, the same second derivative, and the same third derivative. So as you ask for more and more terms, you are asking for a polynomial of higher and higher degrees, which agrees with your function at that point to more and more derivatives. And I'm not going to go through all the details here because, again, this video is not about MacLaurin series, but it ends up looking like this. All of the derivatives appear in the series for that function. This comes from solving a system of equations. You want the function to be equal to the value and the derivative of the function to be equal to the derivative of the series, and so on and so forth. And the factorials here are coming from taking many derivatives of a polynomial. Every time you take a derivative, your exponent comes down as a coefficient. So if it was x to the power of 5, then you have a coefficient of 5, but now the exponent is 4. And if you take another derivative, then the 4 is going to come down, and now it's 5 times 4. That's gradually building factorials as you go through the solution of that system. And the reason why ln is different in that list is because they wouldn't be able to make a series for ln x that is making a polynomial that agrees with ln at x equals 0 because ln doesn't go through x equals 0. That is a vertical asymptote. So they do it at 1 instead. X is still 0, but when x is 0, f of 0 is ln of 1, which is 0. And then f prime of 0, well, the derivative of that is 1 over 1 plus x, which when x is 0, this is 1. So that's why you have a 0 constant term there and a 1 coefficient for the x, and you could go on and get the other terms. Could you do a series for sine of 1 plus x? Yes, but it would be ugly and probably useless. Let's take a look. When x is 0, we have f of 0, which is sine of 1. This is already a bad start, right? We don't know how much sine of 1 is. Sine of 0, we know it's 0. So anyway, the derivative of sine is cosine, so that would be a cosine when x equals 0. That's a cosine of 1. So you see, it's useless because we don't know sine of 1 or cosine of 1. These things are used to calculate approximations. If you do it at 0, then you can calculate sine of 0.1. 0.1 has never been a pretty number. The pretty numbers are like pi over 6 or something, but you're not going to get a good approximation if you are starting from things that you already don't know. Okay, so why were we talking about this again? I remember. We want to prove why that strange looking series for 1 plus x to the power of n makes any sense. So we are going to make a MacLaurin series for it. We are going to take x equals 0 and do all of these derivatives, put them in that formula, and everything is going to work out. So let's start our process here. F of 0 is 1. And now we have to start taking derivatives. But notice that even though there is a composite function here, an n outside of a parentheses with a 1 plus x, the chain rule is not interfering with us. That is very lucky because the derivative of 1 plus x is just 1. So these are correct. And all that I need to do here, here, and there is just to plug in x equals 0 to these things, which is just going to give me 1 to the power of something. And the things that are actually doing anything are just these, which are the numbers that look exactly like those factorials that are not really factorials because they stop at some point, right? F prime of 0 is just n because it's right there. F prime prime of 0 is n times n minus 1, which I'm going to put here on top of the 2 factorial, which is exactly how far the formula booklet goes, by the way. But the next one is n times n minus 1 times n minus 2 divided by 3 factorial. And that's convincing enough to me. So the moral of the story is what? The high-level part of binomial theorem is nothing but a special case of MacLaurin series, the special case of that function over there, 1 plus x to the power of n. Another interesting thing that you can see from here is that even though the binomial theorem high-level part of the formula booklet states that the exponent n needs to be a rational number, it doesn't really have to be a rational number, right? If you wanted to put 1 plus x to the power of pi, for example, which is irrational, this would be exactly the same. There is another aspect of this which I would like to mention. The radius of convergence or the interval of convergence, they're not exactly the same thing. It's like the radius of convergence is sort of the size of the interval of convergence. And I briefly mentioned this earlier today when I said that the sum of an infinite geometric sequence only exists when the common ratio has an absolute value less than 1. So you have this series here for that binomial with the exponent of -1, but it doesn't work for all values of x. And that kind of makes sense, right? Because a power of -1 is a fraction. A fraction has a domain restriction, which is that you can't divide by 0. So clearly, at least x equals -1 would not work here. But it's actually worse than that because we are making our approximations around x equals 0. So when you start from 0 and you go to the left, you get that problem over there at -1. It's like a barrier that you can't cross over. So like x equals -1.1, for example, or x equals -2. They don't cause divisions by 0, but they are also not equal to the sequence in any meaningful way. It's another thing that I mentioned at one point in the video when I was doing an approximation for the square root of 10. You have your powers of x getting bigger and bigger, so x had better be a small number, otherwise this whole thing is not going to converge, which means that the last terms are getting bigger and bigger, so they're not canceling out, they are not becoming irrelevant like they should in an approximation. So, and that happened after passing through this barrier here. So that is a big problem that you have there with the -1, okay? It's not just a problem for that one, it is for anybody that goes after it. But it's even worse than that, because since you started from 0 and the radius, like the distance that it took you to get there was 1, then it's also not going to work if you go more than 1 to the other side. So it's like the barrier works on the other side as well, where it's not even there, but just the fact that there is a barrier at distance 1 from 0 to one side prevents the series from converging after one radius to the other side as well. And you can see that if you put x equals 2, it's not going to work. If you put x equals 1.1, it's not going to work. So for this series, the radius of convergence is 1, and the interval of convergence is from -1 to 1. What about this? This has the same kind of problem, right? Because the square root also has a domain restriction. We can't take square roots of numbers that are less than 0. So it's the same exact picture. We are making an expansion around 0, but if we went to the left so that x was -1, well, -1 could be okay because the square root of 0 is 0, but we can't go past that. So that makes a problem to the other side as well. We can't go past 1. Here's another typical type of exercise, 1 plus x squared to the power of -1. So you know the series for 1 plus x to the power of -1, and all that you have to do now is to substitute the x squared where you would normally have put the x. Easy, right? Composition of functions. But what about the convergence of this series? Well, 1 over 1 plus x squared doesn't have any domain problems. This is never a division by 0 because x squared is always positive. And then we add 1, so it's not 0. I mean, x squared could be 0, but 0 plus 1 is still positive, so I'm not dividing by 0. The only way that I could possibly divide by 0 here was if the x squared was -1 to cancel out with the 1. But this would mean that x needs to be either plus or minus the square root of -1, which doesn't exist in the real numbers. Of course, it exists in the complex numbers, but this whole topic is about real functions. The complex numbers shouldn't matter. This is kind of like when I'm first teaching quadratic functions and I say that the discriminant determines how many solutions the function equal to 0 has. So if the discriminant is less than 0, then your equation doesn't have any solutions. And then a student who knows a lot of stuff asks, no, but it has solutions. It's just that they are complex numbered solutions. And in that context, that doesn't really mean anything because we are drawing a quadratic function with a real number in the independent variable and a real number in the dependent variable. So nobody cares about the complex valued solutions. They don't exist in the graph. They don't interfere with the function. However, in this case, even though we are always working with real numbers, that's a real function, it would have a domain restriction on plus or minus I. So I have to put that in a little picture in the complex plane, and I have to look at my radius of convergence. That is why it's called a radius. We are talking about a circle. We are not talking about an interval. There is an issue in the complex numbers. I don't want to go to the complex numbers. I don't want my x to be able to be I, but that issue in the complex numbers prevents my x from getting out of any side of the circle. X can't be 2 in here either. The sequence is not going to converge. 1 plus 2 squared is 5. 1 over 5 is not this. So listen, if you're seeing this for the first time today, if you're not shocked, I don't know what's wrong with you, because this is shocking. This is the complex numbers interfering in a totally real valued application without having been invited to the party. This is clear evidence that the complex numbers exist just as much as the other numbers. They're not simply figments of your imagination. So I'm going to show you now the pictures of the examples that we've been talking about. This is 1 over 1 plus x. It's the sum of the infinite geometric sequence. And I've asked the software here for a MacLaurin sequence with 10 terms, okay? Of course, if you want to play around and get more terms, a better approximating polynomial, you will get a little bit closer to 1, because you can see in my picture here that the approximation is going wild quite a bit before 1. Something like 0.8 in this picture is already not approximating very well. But if you put more terms in your polynomial, then it will get better at 0.8, it will get better at 0.9, but it will never cross 1. And on the negative 1 side, this is not surprising at all, right? Because you can see the vertical asymptote, and there is no way that a polynomial could ever go through that. This is the more surprising one. 1 over 1 plus x squared, which does not have any vertical asymptotes. Again, I'm using a polynomial of degree 10 here, and you can see in the picture that the approximation is not really good past 0.8 to one side and negative 0.8 to the other side, but it would get better if you put higher degree terms in your polynomial, except it wouldn't cross the 1 or the negative 1. That's the barrier that the complex numbers are creating for it. Because x equals I or negative I would have a division by 0, which is impossible. This is the ln of 1 plus x example. Again, the left side has an asymptote, so it's not surprising that it breaks down there. But it also breaks down to the other side because the radius of convergence is 1. Same story. More terms would make it better, but it wouldn't cross, etc., etc. Now, at this point, it would be fair if you were thinking that this complex numbers story that I'm telling is just me being a little bit crazy, because all of the examples that I've showed you, the radius of convergence was 1. So another plausible explanation would be the radius of convergence is always 1, because we haven't seen an example where it isn't. And the simplest explanation for that would just be what we've been talking about, that since the powers of x are getting bigger, the exponents are getting bigger, then x's that are bigger than 1 tend to break that down, because each next term is going to be bigger than the previous term, so the far away terms are not becoming irrelevant like we wanted it to. That is an explanation that makes a lot of sense, but I'm going to show you an example now where the radius of convergence is not 1. I'm building this example on purpose, of course, because I want something to have problems only in the complex numbers, and I want these problems to be a little bit farther away than just 1. So with that in mind, I've taken this quadratic function with the vertex at the point 1, 1, and I've put 1 over the quadratic function so that the domain restriction is, as you see, calculated here. The x's that are forbidden are 1 plus or minus I. I have put them in a little picture of the complex plane. The distance between the problem points and the origin is now the square root of 2, because it is the diagonal of a square of side length 1. And that's a circle with radius the square root of 2. If you look at it in the real line, the horizontal line, this predicts that the radius of convergence of the series for this function will not be 1, but the square root of 2. I started to attempt to calculate the series here by hand, but it became a little bit messy because the derivatives are not very friendly in this case. So I just asked the software to calculate the MacLaurin series for me to 10 terms again, and this is the result. Already just by looking at it for 1 second and comparing to the previous ones, you can see that it's a little bit larger than the other ones. And if you look at it really closely, you will see that at 1, this approximation already looks quite good. And in the previous examples, the 0.8 was like sort of good, but not good enough with only 10 terms. So this looks already a little bit better. But if it's not entirely convincing, I've also asked it to draw a picture with degree 20, which is this one here. And now you can see that it has clearly crossed over 1, right? The square root of 2 is like 1.4, so we shouldn't expect to see it go over 1.4. And the 1.4 in this picture is looking pretty much like the one looked in the previous pictures. It's like not good, but it's the edge of where it should be good, so that's fine. And just for comparison, here is sine of x with its sequences with degree 10 and degree 20. Because sine of x doesn't have any restrictions. The radius of convergence for sine of x is infinity, which means that with a big enough degree, you can approximate sine with a polynomial like these ones as far away from 0 as you want. That's not the best way to get an approximation for sine because we know it's periodic and we should explore that. But technically, it's possible if you want to do that.